IR correlation table. So the good news is that people have been looking at the IR spectra of organic molecules for about 80 years now. This instrument was invented in the 1930s, 1940s, okay? And so what scientists do is they, they put a molecule in, they look, they say, oh, look, it absorbs here, it absorbs here, it absorbs here. They write that down. Then they put another molecule, okay? And eventually they see the patterns, and then they publish a table. And when we want to use IR, we just look at the table. So that table is called a correlation table. It relates the frequency of the light that's absorbed. It relates it to a structural feature in the molecule, okay? And it's already done for us. You don't have to memorize it. You should always look it up. That's fine. That's what you're supposed to do. Eventually, some of them you'll just memorize because you'll look them up so many times. Does that make sense? Okay, so look. What is it we're looking at then? Well, what we're looking at in a correlation table is two things. First is, what are the atoms in the bond? I'm sorry, three things. What are the atoms in the bond? Second, what kind of bond connects them, right? Because atoms is mass of the balls, right? And the type of bond is how strong is the spring. And then the third thing is what type of vibration, because remember, we have stretching, but then we also have bendings. They work a little bit different, all right? So you can read through this. This is just generally reminding you of things. What I want to do is I want to look at the, I want to just make one point about the correlation table. The correlation table is a guide. It's not a Bible. Does that make sense? Like, in other words, it's not saying it absolutely has to be this way, right? It's saying these are the kinds of trends that we see, and we have to use some interpretation. Okay? In particular, what we see is that while I talked about the balls and springs, there are other things that can affect the way that things might vibrate. One really good example, one that you're going to see, is that you have C double bond O absorption. And the C double bond O absorption we're going to see on the table is usually slightly above 1700 for a frequency. But if we take that C double bond O and we put it adjacent to another pi bond, like a C double bond C, where we go C double bond O pi bond, then we go a sigma bond, then we have another pi bond. We're alternating. We call that conjugation. And we're going to talk about that in second semester in more detail. But one of the things that conjugation does is it weakens the C double bond O. Makes that spring weaker. Remember I said when the spring is weaker, the frequency goes down. So if the frequency was 1700, we make it weaker. Now it's going to go into the 1600s. Okay? Does that make sense? And so very often, for example, we will see a C double bond O vibrate at 1685 because it's conjugated with a benzene ring. Okay? It's next to a benzene ring. All right, let's look at our correlation table. Let me describe this for you really quickly. This is, I modified this a little bit from the one that was in your notes last semester. Oh, somebody just asked me, so V0 equals V1 if the speed is constant.
Oh, that was from the potential energy graph.
Yeah, no, I totally get what you're saying. Okay, so here's the deal. The amount of energy in V0 and the amount of energy in V1 is different. Okay? The potential energy is different. That means that they vibrate to larger distances. Okay? But the frequency is actually a constant. the frequency, the time that it takes them to go from here to there and back is a constant. But in order, obviously, since you're moving a larger distance in the same amount of time, at the bottom, they're going to be moving faster. That makes sense?
Yeah, thank you very much.
So that's how that works. It's a weird thing. If I had someday I'll show you a little thing I can do to show that. Anyways. Okay, so here's our table. I've arranged the table according to the frequency of the vibration, because here's what's going to happen. You're going to have an IR thing. You're going to look, oh, there's a peak here. Here's the number, right? That's what you're going to know. So you're going to start on the left, find a number. Then you're going to look at what kind of bond could that be? What would be in the bond, like a sp3 hybridized oxygen, sp2 hybridized oxygen, and so forth, right? And then finally, I put a little bit of information about the peak. Some peaks are really broad, some are sharp. And then there's also an issue about, you know, the peaks are upside down. I'm going to show you some examples in just a moment. But if the peaks go down a lot, we say they're strong, which is S. And if they only go down a little, we say they're weak, which is a W. And then in between strong and weak is medium. Okay. And it's not perfect because also, like our particular IR instrument zooms so that no matter how big the peaks are, it makes them big. Does that make sense? So if you had all little weak peaks, they would all look like they were strong.